All right, let's get right into it. For a long, long time, the number I, the square root of -1, it kind of felt like this weird algebraic trick, a ghost in the machine invented just to make certain equations work. But what if I told you it wasn't invented at all? What if it was discovered? A number that was basically inevitable thanks to geometry. In this explainer, we're going to see how complex numbers aren't just some math hack. They're the actual language of rotation. Back in school, we all learned about the number line. It's simple, it's clean, it's one-dimensional. Positives go this way, negatives go that way. But that simple idea begs a really cool question. What if numbers could break free? What if they weren't stuck on a line and could exist in a two-dimensional space? What would that even mean? Well, it would look like this. We call it the complex plane, or sometimes the Argand diagram. Just think of it like a regular map, a coordinate system. Our familiar old number line is still there. It's just the horizontal x-axis, which we now call the real axis. But now we have this whole new vertical dimension, the y-axis, and we call that the imaginary axis. So a number like 3 plus 2i isn't just a concept anymore. It's a location, a point on the map at 3, 2. Okay, so before we explore this new 2D world, let's actually take a step back. Let's look at the simple math we already know on that old 1D line, but let's look at it through a geometric lens. Seriously, this shift in perspective is the key to unlocking everything else. Think about it. What does plus 3 actually do? It doesn't just change one number. Geometrically, when you add 3, you are shifting the entire number line 3 spots to the right. 0 moves to 3, 1 moves to 4, -5 moves to -2. The whole thing just slides over. So addition is really just a translation. It's a shift. All right, so what about multiplication? Well, if you multiply every number on the line by 2, everything gets stretched out twice as far from the center. And if you multiply by, say, a half, everything gets squished in closer to the center. So geometrically, multiplying by a positive number is just scaling. It's a stretch or a shrink. But here's where it gets really, really interesting. What happens when you multiply by a negative number, like -1? All the positive numbers flip over to become negative, and all the negatives flip over to become positive. What does that look like? It's a perfect 180-degree rotation around the origin, around 0. And this is the crucial point. Even on our simple little number line, multiplication was secretly hiding the act of rotation. And this right here is such a brilliant way to see why a negative times a negative has to be a positive. Think about it. A 180-degree rotation followed by another 180-degree rotation. Well, that's a full 360-degree turn. It brings you right back to where you started, which is the same as just multiplying by +1. The geometry makes it obvious. So with that foundation in place, let's jump back to our two-dimensional plane. It turns out, extending the idea of addition into 2D is the easy part. It's actually super straightforward. The rule for adding these new numbers is dead simple. You add the real parts together, and you add the imaginary parts together. That's it. And if you've ever worked with vectors in physics or anything, this is going to look incredibly familiar. It's the exact same idea. And geometrically, guess what? It's the exact same action we saw before. If you add a number like 3 plus 2i to everything on the plane, the entire grid just shifts, 3 units to the right and 2 units up. So addition is solved. It's just a 2D shift. No problem. But now we get to the big question, the central mystery of our whole story. How in the world should multiplication work in 2 dimensions? This isn't nearly as obvious. I mean, we need a rule, a system that feels like a natural extension of what we just saw. It has to somehow combine that idea of scaling and, more importantly, that idea of rotating that we found hidden in the number line. How do we build a consistent system for the whole plane? Well, the most beautiful and consistent way to do it is to combine those 2 geometric actions we already found. To multiply 2 complex numbers, you scale the plane based on their lengths and you rotate the plane based on their angles. Put more simply, you multiply their lengths and you add their angles. And this kind of reveals that we need 2 different ways to think about these numbers. That rectangular a+bi way of writing them, that's perfect for addition, because it's all about shifting left, right, and up, down. But for multiplication, it's so much easier to think in polar coordinates, describing a number by its distance from the center and its angle. Why? Because that system is literally built around the ideas of scaling and rotating. So all of this now brings us to the climax. By using this geometric idea of multiplication, we can finally uncover the true identity of that mysterious number I. Let's just ask a purely geometric question, no algebra. On the number line, we saw that multiplying by -1 was a 180-degree rotation. So, what number, if we were to multiply by it, would give us just a 90-degree rotation? Okay, let's track it down. A pure rotation shouldn't make things bigger or smaller, right? So its length, its magnitude, has to be 1. And its angle, well, we want it to be 90 degrees. So where's that point? It's right here, on the imaginary axis at the coordinate 0, 1. Let's just give that spot a name. Let's call it I. So I is our 90-degree rotator. Now for the million-dollar question. What happens if we multiply by I a second time? What is I times I? Geometrically, this just means we do that 90-degree rotation all over again. And what happens when you do a 90-degree rotation and then another 90-degree rotation? You've just done a 180-degree rotation. And where does that land us? Right here, squarely on the number -1. So the geometry forces the issue. I times I has to equal -1. And this is it. This is the big aha moment. That rule, I squared equals -1, it's not some strange definition somebody pulled out of thin air. It's the logical, completely unavoidable result of defining multiplication as rotation in 2 dimensions. The number I is, at its heart, just a quarter turn. So, we found this absolutely beautiful geometric system. But you might be wondering, is it just a mathematical curiosity? Is it just a neat party trick? Absolutely not. This rotational property is what makes complex numbers one of the most powerful tools in all of science and engineering. I mean, being able to handle both a magnitude and a rotation in one single number, it's a total game changer. In electrical engineering, it's how you analyze AC circuits. In signal processing, it's the entire foundation of Fourier analysis, which breaks down complex signals into simple rotations. And in control theory, it helps keep everything from airplanes to thermostats stable. And the results in pure math are just profound. By adding this one extra dimension, we get this incredible property called algebraic closure. The fundamental theorem of algebra basically says that once you allow for complex numbers, every single polynomial equation has a solution. There are no more impossible equations left to solve. The system is complete. So you see, complex numbers aren't really imaginary at all. They are the inevitable, complete system for what numbers look like in 2 dimensions. They were always there, just waiting to be discovered. And it really makes you wonder, if they so elegantly solve an equation that was impossible on a simple line, what other impossible problems are just waiting for them to unlock?